Okay, welcome back everyone. In the second part of our vector math review, we're going to talk a little bit more about unit vectors and components, and then also the dot and cross product. So what we're trying to learn from this video is how do you calculate the dot product of two vectors and what does that mean? And then the same thing for a cross product. How do you do it and what does it signify? And then finally, what is a unit vector? So in 3 dimensions, we can think of 3 components for vector A: AX, AY, and AZ. And we'll have 3 components, but we'll have 2 angles: a so-called polar angle, which is theta, and an azimuthal angle, which is phi. So phi is kind of like your longitude as you go around a globe, and theta is kind of like your latitude, but it's measured from the pole down as opposed to from the equator up. And what we can do is we can break a vector into components using unit vectors. So unit vectors are quantities that specify a direction. So they have a length or a magnitude of 1, and they usually point in the x, y, or z directions. But sometimes we can have things that point in the r hat direction, so the radial direction. We can even have theta hat or phi hat. You can have any sort of direction you want for unit vectors, but these are the 3 most common for AP Physics. And so there they are. There's I hat, j hat, and k hat, which all have a length of 1, and they go in their respective directions. And so what we can do is we can use, instead of magnitude and direction, we can use unit vectors. So if I have a displacement of 30 in the plus x, and then 60 in the negative y, and 40 in the plus z, I can write that as 30 I hat minus 60 j hat plus 40 k hat. Or you can even shorten that more, put brackets around it, and just put the components, so 30, negative 60, and 40. We do want to include units, so meters, but most of the time you're going to see me writing things like this. So how do you add vectors using unit vectors? It's very easy. You add all the i's together, all the j's, and all the k's. So for example, if A is 3i plus 7.5j, and B equals negative 5.2i plus 2.4j, find C. Okay, well C is just going to be 3.0 minus 5.2 I hat plus 7.5 plus 2.4 j hat. So C is just going to be negative 2.2 I hat plus 9.9 j hat. So it's really not too tough to do that. So now let's talk for a moment about the dot product. We're going to be using the dot product quite a bit, and what it does is it tells you how much of one vector is parallel to another. Another way to think about this is that the dot product of A and B is the projection of A onto B. So, for example, if I have vector A right here and vector B, then A dot B is how much of A is parallel to B. Now the dot product turns 2 vectors into a scalar. We'll talk about this process in a second. And what it does for us is it allows us to calculate things such as work, power, and flux. These are just 3 examples of what we can do with the dot product. So we'll see some examples of this a bit later on. So here's a definition. There's a couple of different ways to write it mathematically, but if we have 2 vectors A and B, where A is AX I hat plus AY j hat, can't really tell that's a j, plus AZ k hat, and B is equal to BX I hat plus BY j hat plus BZ k hat, then A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them, which is also equal to the sum of the product of the components. So ax times bx plus ay times by plus az times bz. So for example, let's say that we have vector A is 6i minus 7j, and vector B is equal to negative 3i minus 4j. And we want to find the angle between these two vectors. How do we set that up? Okay, well, we know that A dot B is going to be equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And that angle is what we want. And we also know that this is equal to ax bx plus ay by. Whoops, I was thinking about z because there's no z component. So it's ay by. So then we just evaluate this. First of all, the magnitude of A is going to be 6 squared plus 7 squared, which is 49 plus 36 is 85, right? That's square root of 85. And so that goes in for magnitude of A. Okay? And then we have the magnitude of B is going to be just 5, because it's going to be 9 plus 16. So square root of 25 is 5. Then we have the cosine of the angle is going to be equal to ax bx, so that's going to be 6 times negative 3 plus negative 7 times negative 4. So that turns out to be negative 18 plus 28. That's just going to give us 10. Okay, and then on the other side, we're basically going to have 85. I don't think we can really break that down, but it's going to be 5 root 85 times cosine theta, and we'll just calculate that out real quick. So that's going to be about 46.1 times cosine of theta is equal to 10. This means that the cosine of theta is 10 over 46.1. And it's getting hard to see that color, so we'll just use white. So this means that theta is the inverse cosine of 10 over 46.1. And that gives us about 77.5 degrees. And we want to check that and see if that makes sense. We'll just kind of plop down a real quick graph. And so vector A is going to be 6 in the i-hat direction and negative 7 in the j-hat, so roughly this way. And vector B is going to be third quadrant, so minus 3 and then minus 4, so roughly like that. And this angle here is going to be not quite 90 degrees. So 78 is pretty reasonable for that answer. Okay, so that was the dot product. The cross product gives us a vector which is perpendicular to two other vectors. It's often used in math and also in physics to find a vector which is perpendicular to a plane. So we use it to find things such as torque, angular momentum, and the direction of magnetic forces. So we're first going to encounter cross products when we get to chapter 9 or so, but it's important to talk about it now because a cross product takes two vectors as its input and gives us a third vector as the output. Put another way, if A has these components like before and also B, then we have to evaluate the determinant of A cross B is equal to this. So this is a matrix determinant that we are going to evaluate. And I've written it out, but one way to do this is sort of to cover up I hat. So we're multiplying by I hat, and we're taking the determinant of these four. So that's AY, AZ, BY, BZ. Then we cover up J, and we have AX, BZ, AZ, BX times J hat. Whoops, and there should be a negative sign there. And we're going to cover up K hat and do the same thing. So we're expanding the 3 by 3 matrix, and you might remember from math class that when you do this, that there's an alternating series depending on what you cover up, and you have to take that into account, which I forgot to do here. So really, we have to have a minus sign for that second component of the expansion. So we'll make sure to do that in our example. Okay, so here it is written out, and again, I seem to have forgotten that all-important minus sign. Okay, and the other thing to keep in mind here is that we can calculate the magnitude of the cross product by thinking about the area of a parallelogram with A and B as the two sides. Okay, so we'll take the same two vectors as before, 6i minus 7j, and b is 3i minus 4j. But actually, we want to show how this works out in 3 dimensions. So we're going to call A 6i hat minus 7j hat plus 2k hat. And vector b is going to be the same thing, negative 3i hat minus 4j hat minus 5k hat. We want to calculate vector c, which is a cross b. Okay, so we set up our matrix here. Okay, so c is a cross b, which is equal to, we put I hat, j hat, k hat, and then our components, 6, negative 7, 2, negative 3, negative 4, negative 5. Now the other trick to do this is to rewrite the first 2 columns and then to do kind of this weird multiplying down the columns or diagonals thing, but I'm not going to do that right now. Okay, we're going to stick with our evaluating. Okay, so C is going to be equal to I hat times, so I cover up my I hat components, and that's going to be 35 minus negative 8 I hat. And then I put my negative sign, and I cover up my j, and I'll have negative 30 minus negative 6. And cross products are notorious for mess ups with signs, so you have to be very careful. It turns into a plus. And then we'll have a plus again, and we'll have k hat, and we'll have negative 24 minus 21. So this means that our final answer is going to be 43 I hat. Now this is going to give us negative 24, but it gets another negative sign in front. So plus 24 j hat minus 45 k hat. Okay, and we can check this out sort of in a 3D picture, but it does check out. So this is the correct answer for our cross product. Okay, so that's been our review of vectors, and then if you keep following with our videos, we're going to start talking about one-dimensional motion. However, if you're studying electricity and magnetism only, you're going to want to skip to the electric charges and fields videos.